All right, looks like the recording is going. So, welcome everyone. This is the first GAIA technical seminar. Tonight is electronics, and then we'll be doing on Wednesday the generator as well as like the full system analysis. And then on Thursday, we'll be doing the blades. And so let me get the screen share. And for anyone who wants to follow along with the slides, I sent the link to the view only slides in the Slack in general. So right, let's get started. So when you often think of a wind turbine, electronics are probably not the first thing you think of. The blade and the tower are much more visible, but electronics are, of course, really important for wind turbines. Three major tasks that electronics do: the power conversion, probably the biggest part. You need to convert the kinetic energy to usable electric energy for households to use. In this particular case, the electric load on the system is LED lights for the most part, and occasionally phone chargers or other small devices. And the second task for electronics is energy storage, so that in periods of low wind, the family is still able to have enough energy to power their needs. And finally, monitoring and like general other low voltage type of control, sensing, etc. And so this will be an outline. We'll go through those three systems. The bulk of the focus of this presentation will be on the power system, because that's typically the type of electronics that people have the least familiarity with. The storage and monitoring people are more likely to have been acquainted with stuff like that through Arduino work, stuff like that. And so I'll focus on the power system, and then we'll do storage and monitoring. And so within the power system, we'll talk about rectification, power maximization, charge control, and then also describe the baseline solution. So in the power system, the baseline solution that WindAid currently uses for their controller is a commercial off-the-shelf joint wind and solar controller that they buy off of Alibaba, and it's a product that ships from China. And the datasheet is linked there. That's also linked in your technical resources spreadsheet. And this is a major pain point for WindAid. The price of the controller itself is only about $100, but because it is imported internationally, they accrue up to another $200 in transportation and taxes, so like tariffs, import fees, stuff like that. And in addition to the monetary problem, because it's not locally sourced, that makes it so much harder to maintain or repair. And so WindAid is asking teams to find a locally sourced alternative so that whatever controllers can be made with parts that are more readily available within Peru. And so sort of two different paths that you could go down this design would be a fully custom design that is available from component parts that are all available locally, or the creative use modification somehow combination of starting with a locally available product that might be intended for other purposes, and then adding onto it in some way so that it fulfills the requirements of this wind system. And so this controller performs three functions: rectification, power maximization, and charge control. Rectification means conversion of AC to DC. And the generator that Windage uses is a 3-phase AC generator, permanent magnet generator. And we want that electricity to be converted into usable direct current, which is what they currently use is a battery. That's 12 volts DC. And the current controller does not actually specify in its datasheet how it achieves rectification. My guess is that the architecture is either an H-bridge or a 3-phase inverter. It's almost definitely active and not passive. And I'll define what all those terms mean on the next couple of slides. But that's how we actually don't know very much about how the existing solution performs its rectification. The second feature is power maximization. So the controller has the ability to adjust its impedance, or like the amount of resistance to electricity flow it presents, so that the turbine will spin at a particular rotational speed. And because of aerodynamics, there is a singular particular rotational speed for a given wind speed that will produce the most power. And so we want the controller to be able to find that rotational speed, which will change depending on the wind speed, and make the generator spin at that correct speed so that we can be generating the most power. And the way that the existing controller does this is with a thing called MPPT, maximum power point tracking. And we'll also talk more about what that means on a later slide. And then the final function is charge control for the battery. So the controller needs to be able to figure out when the battery is full, then you can't obviously keep charging it. And so it dumps power currently to an external resistor. They're big green external resistors that are often called pickles. They're like power resistors. And then another part of charge control is even if the battery isn't full, depending on the battery's voltage, there are certain current limits that will need to be enforced to keep the battery healthy and safe. And then we'll go into more detail on all of these things. Let me make sure there's no questions in the chat. Okay. And yeah, feel free to interrupt at any time if you guys have a question. So, rectification. I made a little table of the different types of rectifiers that you might see out there. They can generally be categorized whether they're passive or active. So that's based on the type of switch element that they use. And then based on the, I guess, like architecture of the direction of power flow. So they can be single phase unidirectional or half bridge, single phase bidirectional or full bridge, or 3-phase. And a synonym for full bridge is H bridge, which can get kind of confusing because H does not stand for half. The letter H is similar to the shape in the circuitry of a full bridge rectifier, so that's how it gets that abbreviation. And so another point of potentially confusing terminology that I'll point out is the word rectifier versus inverter. If you're thinking about the definition of a rectifier, to rectify means to change AC to DC, and to invert means the opposite, to change DC to AC. But inverters can also perform rectification by working in reverse. So in this case, we want to perform the process of rectification, and we can perform that process with a rectifier, which is a way of like passively doing rectification, or with an inverter, which can both invert or it can rectify. And it's a little bit of just what words are typically used. That the inverter is performing rectification, but because it's active, people just call it an inverter, even when it's performing rectification. And so, let's see, passive. The switching element in a passive rectifier is a diode. And so diodes, because they only let current flow in one direction. They act as one-way switches, but you can't control when the switches are on or off. They will sort of control themselves based on the properties of the diode, based on like whether they have effectively a positive or negative voltage across them. And so because you can't control the state of the diode directly, the only way to control the current in one of these rectifiers, which we want to do in order to extract power from the generator, the only way to control the current is by changing the load impedance. And impedance, again, referring to the resistance, or also there's imaginary counterparts to resistance, which are called reactance, but I don't think we need to get into that too much. Basically how much resistance there is to electrical flow on the load. In this case, the battery, the thing that we're charging. And then the active rectifiers have a lot more flexibility because instead of diodes, they use controllable switches. There are different types. Typically, they'll either use FETs or IGBTs. And so those stand for, let's see, field effect transistors and insulated gate bipolar transistors, I believe. And so those are switches that you can control with a microcontroller. Has some logic that you want your switch to be on or off, and you can set it that way. And these controllers are able to control the current going through the generator by changing whether those switches are on and off. So specifically, they're adjusting the timing and duration of these PWM pulses. PWM stands for pulse width modification. It's just the phrase that means this type of voltage control in order to match a certain voltage set point that a controller might decide is the desired voltage. And then these active controllers have different schemes of how they decide what they're PWMing. And so there's what's called the modulation scheme. That is directly when should a particular switch be on or off. And a couple of examples of different modulation schemes are 6-step modulation, sign modulation, space vector modulation, that one's also called SVM, and overmodulation. And I won't get into exactly the differences between all of them. If you guys end up needing to like more resources on deciding like the pros and cons of different modulation schemes, feel free to ask it in the Slack. But for now, just suffice it to say that there are different ways of setting those pulse width modification, those PWM waveforms to control the voltage and therefore control the current in the generator. And then the thing that sort of is behind the modulation scheme is a control scheme, which is a more high-level function that decides what command to send to your modulation scheme. So the modulation scheme works in the hardware of like which switches should be on or off, and the control scheme is a little bit more high level in the software. There's abstractions. Examples include 6-step control, which is typically just used with 6-step modulation, or the really common one, field-oriented control. And you can also perform field-oriented control in a sensorless way. Typically, field-oriented control requires a position sensor of the motor or generator shaft. But sensorless control is a way to get around that. So that even if you don't have a sensor, you can in software still figure out how to control it. And that was a lot, so I'll pause for if there's questions. I also have the next slide will show pictures of all of these. Okay. So here's pictures of the different kinds of rectification circuits. So you can see that the passive ones are all using diodes. In this case, using either 1, 4, or 6 diodes. And so the 3-phase is obviously the most complex. It uses the most parts. And then the active circuits use switches, and in some of them also use separate diodes, like this image shows 2 separate diodes. And those switches, as mentioned before, could be FETs, could be IGBTs. There are other sorts of fancier switches that are probably not as well suited for this project. And so, what else can I point out here? The complexity definitely gets higher as you go to the right and as you go down, but also the amount of power you can extract from the generator. The amount of power you can extract gets higher as the complexity of the circuit gets higher. And then as you're learning more about these voltages, especially AC voltages, can sometimes trip people up with terminology. And so there's a couple terminologies that I'll run through. The first is if you're asking the question, which 2 points are you measuring the voltage between? And depending on the answer to that question, you might be measuring a line-to-line voltage or a line-to-neutral voltage. And so there are pictures here. These are showing an abstraction of the 3 phases of the generator. So like the pieces of copper wire in the generator are connected either in a Y connection where they're all connected at the center, or a delta connection where it's like the triangle shape. None of them share a node, all 3 of them. They're all just connected to one other node. And so in the delta connection, there is no common point between all 3 phases. So there is no neutral point really. But in the Y connection, there is a neutral point. That's that center place where all 3 wires are connected. And then you've also got phase A, B, and C. And so when you have a Y connection, if someone is referring to a line-to-line voltage, that would be the 208 volts in the picture. So you would be measuring between phase, for example, A and B, or any other phases. And because the phases are balanced, the voltage between any 2 phases is all going to be that same 208. And this is something that can be tricky if you haven't worked with AC before, because you might think like, oh, if A to B is 208 and B to C is 208, then you might expect A to C to be 416, but that's not the case because they're AC, because they're not DC voltages that you can just add. They're a sinusoid, they have a phase shift, and so it works out that because they're all 120 degrees out of phase from each other, the voltages between each one will all be the same, will all be 208 volts. And so that is line to line. And to make things even more confusing, sometimes that is just called line. And the line to neutral, on the other hand, would be what is labeled 120 volts in this picture. And so it's just from any one of the phases to the neutral point in the middle. And those are also going to be all the same voltages, also going to be 120 degrees phase shifted from each other. And then on the delta, it's a little bit simpler because you don't have to worry about a neutral point. But the delta has other downsides that you can get weird current flow that I guess I won't go into the details of. But I think this Y connection is a lot more common in generators that I've seen. And another terminology that can trip people up with AC voltages is related to the amplitude. So here these voltages are labeled just 120 volts, but we don't know, is that 120 volts RMS, 120 volts peak, or 120 volts peak to peak? And typically in like US power systems, at least, I know that that's typically referring to the RMS voltage. And RMS stands for root mean squared. And you can see it on this picture. It's a measure of equivalently how much power, in a way, the voltage signal has. And if your voltage signal is a perfect sine wave, the RMS will be a factor of the square root of 2 lower than the peak. And the peak voltage is what you typically refer to as like the amplitude of the sine wave. So that would be going from whatever the 0 point is to the max point. And then peak to peak is going from the min to the max point. And so it can just be tricky when you see voltage ratings for different AC components, and something might be some amount of volts peak to peak or some amount of volts peak, and you need to be able to translate between them. So like the factor of 2 between peak and peak to peak, and then the factor of square root of 2 between RMS and peak. Oh, and I guess I forgot to mention on this slide, the factor to convert between line to line and line to neutral is, I believe, the square root of 3. Does that work out? I think so, yeah. So 120 times the square root of 3 gives you 208. And so you can end up having a lot of like factors to make sure to keep straight. So that's it for the rectification side. I can now move on to power maximization, but I'll give people a chance to ask questions if they have any. So power maximization. So we mentioned that there is a specific rotational speed that the generator ideally should be rotating at in order to extract the most power. Where does that come from? This graph shows the power as a function of tip speed ratio, which is lambda, for different blade designs. And so these are determined purely based on the aerodynamics of the blades. And the curve for the default Windade design is shown in green. And you'll hear more about like where these curves come from in the blades technical seminar, but for now, just take them for granted that they exist. And we can see that for the Windade blade, we want a tip speed ratio of about 6.5 to maximize the mechanical power. And so what that tip speed ratio is the ratio between the linear speed of the blades, like as they're going around, the rotational speed, so like the omega times r, the ratio of that to the wind speed. So we want the omega times r of the blade rotation to be 6.5 times larger than the wind speed. And typical wind speeds are maybe like 3 meters per second, 4 meters per second, 5 meters per second in Peru. And so we want that tip speed to be maybe 20 meters per second, let's say. And so with that 20 meters per second and then the radius of the blade itself, you get the omega, and you have a certain RPM that you want the generator to be turning at. And that RPM will depend on the instantaneous wind speed, which obviously changes over time with the weather. And so how do we get the controller to track that different RPM? It The current controller uses what's called MPPT, maximum power point tracking. They perform real-time model-free optimization to maximize power. MPPT algorithms really came from the solar industry, not so much wind. It's a very common thing that solar controllers all run off of MPPT because they are basically adjusting the impedance of the circuit so that, because photovoltaic cells have a certain relationship between their voltage and their current that also depends on the instantaneous conditions, stuff like temperature. And so solar really leads the way with this MPPT controllers, and you can also use them for wind. What it means, these terminology, real-time model-free optimization, that's to contrast it to other ways of trying to do optimal control. That, for example, there are other ways that might have a model of, you might encode this graph that would be model-based instead of model-free optimization. And that type of controller might, for example, write a PI loop to regulate the tip speed to 6.5, to the tip speed ratio to 6.5. But the downside of that type of controller, a model-based controller, would be that if this graph is wrong, then you have no way of like really knowing. Your controller will just go to 6.5 no matter what. And if it turned out that the actual optimum tip speed ratio was more like 7, you would never have a way of like adjusting for that. And so the MPPT adjusts for that because it doesn't rely on a model of what the optimum tip speed ratio should be. It figures it out itself in real time by one algorithm. It can use different algorithms, but the simplest algorithm is perturb and observe. And so you can imagine this as the controller chooses an arbitrary tip speed ratio to start out. Let's say it chooses 6, and then it perturbs in a certain direction. So let's say it chooses to perturb down first. It perturbs and now it's at 5.9. And then it sees, oh, I'm getting less power at 5.9 than I was at 6. That's not the right direction to be moving in. So let's perturb in the other direction. So it goes up to 6.1. And it's like, yes, good. I'm getting more power than I was at 6. Let's keep going in that direction. Then it goes 6.2 until it eventually converges on 6.5. And so it's basically doing a sort of like gradient descent in real time, if you're familiar with that algorithm from like computer science. And it's able to adjust even if like suddenly, because of a change in conditions or whatever, the optimal tip speed ratio used to be 6.5 and now it's suddenly 7. The perturb observer will be able to figure that out and like change itself and then change itself back as needed. And the potentially tricky thing about that perturb and observe, there's no need to like tune gains like you would in a PID controller. But the thing that you have to tune is the step size. Because imagine if it took a step size of 1 here, instead of 0.5, like it started at 6 and then it tried 7 and its perturbation. And then it would see that like, oh, the power at 7 is slightly lower. So that's the wrong direction. But actually it was the right direction. It just skipped over the actual optimum. So you want to tune the step size so that it's small enough that it doesn't like miss things, but not so small that it gets caught up in, if there was like a super small local maximum, a local spike, you don't want it to get caught in one of those. So that's the main thing to think about if you end up writing your own perturbator controller. Or I'm sure there's probably different libraries out there that implement it. And yeah, there's no need to know the optimal tip speed ratio ahead of time. But if the blades are well characterized, and if we're confident in, for example, if this were an experimental relationship between tip speed ratio and mechanical power, perhaps it would be suitable to have some sort of model-based controller instead of a model-free controller. And so there's different ways that in your design you could implement that. And then the third function of the controller, the final one being charge control. And so the current solution, as we said, uses a 12-volt car battery. That's a lead acid battery, but different battery chemistries will have different requirements for what like kind of charge control they need. And lithium batteries are going to be a lot more sensitive to this than other battery chemistries. And so charge control needs to protect the battery from overvoltage and undervoltage. So that would be the same thing as overcharging and under discharging the battery, as well as overcurrent. So making sure that if it's super windy and the turbine is generating more power than the system can handle, it needs to divert some of that power away and into a resistor to burn it off if the battery can't handle that much current. And then finally, over temperature, which some of the cheap charge controllers probably don't monitor temperature, but that's a thing that you might often find in a charge controller. And in the charging process, especially for lithium batteries, they'll typically have, besides protecting from all these like fault conditions, they might also have a controller that basically adjusts how much current is coming into them based on how close they are to being fully charged. So when they're sort of in the middle region or like close to empty, they'll charge at constant current. And then when they're getting close to being full, they'll charge at constant voltage instead of current. The reason for that is batteries have an internal resistance, and so there will be a voltage drop over that internal resistance of the battery when you run a current through it, because V equals IR, Ohm's law. And so if you kept charging at constant current, the voltage that you would measure across those batteries would include the voltage drop and therefore would not be an accurate representation of the voltage that the battery was actually charged to, because as soon as you turned the current off, the voltage was changed. And so this type of algorithm where you transition to constant voltage charging will slowly decrease the current more and more as you get closer and closer to full charge, so that you get closer and closer to measuring the actual voltage to make sure that you're not overvolting the cell. Because overvolting a cell is, for lithium batteries in particular, the main way that they would catch fire. And that's obviously undesired. For the windy batteries in particular, it's really important that the battery safety is well managed, because these are like in people's homes, often right next to bedrooms. And so that's an important engineering requirement. Alrighty, and then another thing I'll mention about the controller is just making sure that it's compatible with all the other components in the system. So in this case, the generator and the blades. You'll mostly want to look at component ratings, so the voltage rating and the current rating being the two primary things to think about. That just that any components that are used in a controller need to survive the expected voltage and current that will be applied to them coming from the generator. And the voltage rating is different AC versus DC. So that would be a thing to be sure to check for safety reasons or also component failure reasons. And then this one is a little bit harder to explain, the switching frequency. So we talked earlier about PWM, pulse width modulation. And PWM essentially applies a square wave of voltage, and that square wave has a particular frequency. And it's a requirement that frequency is fast enough compared to the frequency of the AC voltage that you're trying to rectify. And that latter frequency is called the fundamental frequency. And so that would be a property of the generator. So when the generator is spinning at its maximum mechanical speed, and based on how many magnets or how many poles the generator has, that will determine the frequency of that like electrical waveform. And that's the fundamental frequency. And so in order to be compatible, the controller needs to have a switching frequency that is faster than the fundamental frequency of the generator. And that's because the PWM is in some ways trying to approximate a sine wave with only access to two voltage levels, like off and on. So if you're trying to approximate a sine wave with only a square wave, that square wave needs to be sufficiently fast so that you can sort of approximate those middle levels of voltage by the filtering effect of the impedance of the generator itself. And sorry, that might not have made sense if you aren't familiar with like generator modeling, but the simple version is the switching frequency just needs to be fast enough so that when you sort of filter it through, you can still get this good representation of the voltage that is necessary for the generator at that fundamental frequency. And then diving into what design choices you could potentially explore for this challenge. In exploring the idea of a locally manufactured custom solution, so there are open source three-phase inverters. Some examples of them are VESC and O-Drive. They're often used for like hobby communities in robotics or like electric skateboards, cool stuff like that. They perform field order control. That's the name of their control scheme. And I believe they do space vector modulation, both of them, as their modulation scheme. And so those are examples of like things that could be leveraged, but those things are not like manufactured in Peru, obviously. And so it might be like leveraging those designs or pieces of those designs, both the hardware and or the software, to make something that is more well suited to being manufactured in Peru. And then the second thing, I have a link there of someone who built an Arduino half-bridge inverter for a turbine, a Piggott turbine, so like a turbine in the style of Windaide's turbines. And let me actually go to that link. Hopefully the screen share is still working. It doesn't seem like it's loading, so never mind. But anyway, so that's an example of a custom solution that someone has designed specifically for like a developing context. And so that could also be used as inspiration. And then the other possibility of like a design path would be, instead of making something from scratch, would be adapting a locally available product. The GAIA organizer team has a couple of members actually right now in Peru working with Windaid, and so they've been helping us to check out like what types of products are locally available that could be used by teams. So far, they haven't had too much an opportunity to look, but they haven't found any so far. But I suspect that we'll be able to find some sort of VFD that's a variable frequency drive, because those are commonly used in controlling pumps and fans, things that are used for like HVAC equipment, as a device for rectification, or potentially finding a solar controller that performs rectification as well as performing the optimization. Like those typically have MPPT algorithms in them. And it seems a lot less likely to find something that is off the shelf that would be able to work for battery charge control, but it's a possibility. And so we'll definitely keep teams informed about like other supply chain stuff as we gather more information about them. And I guess we also don't want to limit it to these two solutions because the ultimate problem is that WindAid is having to pay like exorbitant amounts for the international shipping of these controllers because they're manufactured in China and not in Peru, and that they're not repairable. And so if you can think of a way to solve that problem without even designing any new hardware or modifying any other hardware, that like maybe there's just some information that is missing about the customs process, or maybe there's this exact same type of commercial off-the-shelf controller that can be found within Peru, and that wouldn't need to be sourced internationally, that we were just missing initially. So those type of options are also still on the table. Anything that you can think of. And then we just wanted to give an update on supply chain. So actually today, the GAIA students who are in Peru visited Yimsac. I'm not sure if that's how it's pronounced. It's the biggest electronics store in Trujillo, which is where the WindAid workshop is. And it seems these are all pictures that they just took today. They have Arduinos, sensors, LCD screens, lots of like generic parts. So those you can see are like headers, some switches, buttons, and they have a list of a lot of their inventory on their Facebook page. And so we think that that can be really helpful for teams to know like what can be locally sourced, as well as what cannot be. And again, we'll share more information on this as soon as we have it as well. All right, I'll pause there for any more questions about the controller, and then in our last part of the talk, we'll get into storage and into the electronics monitoring. Okay, no questions. All right, then I'll have Charlie, if you're still there. Do you want to take it away with storage?
Yeah, thanks, Becca. So I'll just talk about the storage system for the WindAid system. In any renewable system, energy system, it's really important to have a battery in place because you want to be able to turn on the lights and charge your phone, like for solar when it's at night or when the wind's not blowing. So the battery is a pretty massive part of the system. The current system now that WindAid uses is just a car battery. It's a 12-volt deep cycle lead acid, solid state car battery. There's one per turbine. Sometimes during the raining season, they lose their charge, but they're fairly reliable. They kind of get the job done in terms of their energy storage. They're difficult to transport given their heavy nature. Additionally, they're just for reference, they're stored around 1.5 kilowatts of energy. That ballpark, and so that's about 4% of what an American household uses. So just we kind of get the understanding of numbers. Yeah, give me the next slide, Becca. So the pros and cons for the system. Pros, it's easy to source. You get car batteries anywhere in the world. There's acceptable amounts of storage, is what the people in Peru told us. It would be better if it could be increased, but that's not one of their main priorities. Low upfront costs, like I said, they're easy to source, easy to finance initially. They're compact. However, the big issue is that they degrade over 2 to 3 years, and so wind data is constantly having to buy new batteries, replace the system. They're hard to recycle, so our goal is to increase environmental sustainability. It's not great if we're throwing out these lead acid batteries. And they have decent efficiency in terms of how much energy going into it will come out. So I'll kind of run through a couple of potential alternatives to the system that maybe you guys could take on if you were interested by it. So these three are lithium-ion batteries. I'll talk about pumped hydro energy storage, which is pretty popular energy storage in renewables, and flywheel energy storage system. So a lithium-ion battery. These batteries are getting more and more popular. The cost is starting to come down, but they're still more expensive than the lead acid batteries. They have a higher depth of discharge. They run more efficiently. If you're comparing the lead acid battery to the lithium-ion battery, it lasts 3 times as long, many more charge cycles. They weigh less, but as I said before, they cost more upfront, but then in the long term, they seem to be a better investment. So Windate actually studied if this would be better storage system in 2018, and they recommended that they implement this change. It was like a research paper, but they never actually enacted this change. So yeah, because of their deeper cycles, these might be a better energy storage system, but that would be something that you guys could definitely explore. And next we'll talk about pumped hydro energy storage. This is kind of a lofty idea. This is usually used for bigger storage systems where you use potential energy of holding water up gravity as a battery source. And so when you have excess energy, you pump water up until a hill, and then once you need energy, you discharge it down through this series of pipes, and then use a turbine to power your electricity. So I mean, these are really massive projects typically. They're on the scale of tens of megawatts. It's a very mechanical oriented design, but I think that this also could be something that you guys could explore in terms of a smaller hydro battery. Yeah, and lastly, I'll talk about flywheel energy storage systems. This kind of uses in a car, or an automatic watch. In terms of, just the inertia of spinning a flywheel is what maintains the energy in the battery. So whenever you have excess energy, you spin the wheel faster, and then once you need it, you can use a frictional brake to extract the energy somehow. These are tricky because you need a near perfect vacuum inside the chamber, or else energy will leak out. It'll discharge. They're not readily available off the shelf, so they'd have to take some engineering thinking and manufacturing. And even with a perfect vacuum, they're not 100% efficient. And so it'll slowly drain energy throughout the day. But this is another battery system when it explored. They haven't gone with it, but definitely something you guys could dive into if you're interested in it. Thanks.
Well, then we'll pause again for any questions on storage stuff.
Do we know like the current amount of energy produced per day and then like consumed as well? Because it was compared to like the average American household, but I'm curious if that's different than like a rural household.
Yeah, it's definitely going to be a lot lower. I don't have the energy off the top of my head, but the power of the turbines is about 300 watts electrical, or 250 watts electrical. And so whatever that would be times 24 times some capacity factor, because it's not producing its peak power all the time, would be the amount of watt hours that it produces per day. But yeah, so these we do also have the load cycle, which is not off the top of my head, but should be in one of the rows of the technical resource spreadsheet. That basically the rural families will typically use a couple of LED light bulbs, 12-volt LEDs, as their main load on the system, and then phone chargers, which typically run at 5-10 watts, and then the occasional household appliance. That would be if the family chooses to add on an inverter to the system. So an inverter, different in this context than the thing that controls the generator, but an inverter in this context being a thing that plugs into the battery, and from that 12 volts makes whatever the grid voltage is. I'm forgetting what it is in Peru, but in the US 120 AC. So that you can plug like a blender or a fan or something into it. And so, yeah, sorry that I don't know those numbers off the top of my head, but those are definitely requirements that will go into sizing the energy storage, and so important to keep in mind. Yeah. And I can look after this to see if I can find exactly which document they're in that technical resource spreadsheet.
Thank you.
Alrighty, so monitoring system. So Windy does not currently have any sensors that they install with their turbines. They've used sensors for various like engineering projects over the years, but they're not standard install into houses. And so sensors help to provide useful data for engineering iteration and diagnosing problems. And then less so on the logging side and more so on like the real-time sensing, the ability to alert families to an impending low battery. So the existing Windade electronic system has a little screen that, if you were to look at it, shows the voltage of the battery. But if you're just going about your life, you're not probably going to be looking at the screen every day unless you really have a reason to. And so it's helpful to have an alert that's basically saying the battery is almost low. The battery's low, it's almost going to run out, so that the families can plan their power use accordingly if they know they're going to not have much wind in the next couple of days because the weather forecast, or if they're going to be using more power than usual, they can plan accordingly, or just based on how much power is left so that they're able to use that power wisely for their electricity needs. And so as we mentioned, it's not that often that the batteries will lose charge and like be empty, but sometimes during the rainy season when it isn't very windy in Peru will be when that happens. And so that's one of the things that Windade is asking for, is some sort of buzzer system that, for example, might beep once an hour or something to alert people that the battery is almost out, and then have the ability to turn off that buzzer, for example, if you need to sleep and you don't want it waking you up. And so a sensing system would include ways to sense voltage, current, the wind speed, so an anemometer, some sort of microcontroller, way to log and then store or transmit the data. And so the previous project that Windade had done maybe 5-6 years ago is called the Ramona project, and that stands for remote monitoring. And so this was a completed project, and did end up capturing and logging some data from the turbines, but now is out of service, and Windade doesn't seem to like have it still functioning around. And so there is a lot of documentation that's again in the technical research spreadsheet about the Ramona project. But it's currently not a part of Windade's like standard install. It provided power data, it provided wind speed data, accurate to the location of interest. That's especially important because, for example, the height and the specific location of the topology of like, are there hills around, are there houses around, can really affect the wind speed compared to what you might see just in bulk from like a large wind speed map. And then providing alerts onto like an Internet of Things website was what it did. One of the problems with this system was that it used basically a self-service plan to transmit the data, but that required a continual monthly fee, which ended up getting really expensive for Windade and is one of the reasons why the solution like fell out of use. And so a sensing and monitoring and alert system, we want it to be like the other systems, to be cost effective, reliable, intuitive to monitor, easy to implement, and not negatively impact the functionality of the turbine. That includes not drawing too much power that it would, be an unwanted, like, substantial parasitic load, using too much energy. And Windade, we do want to point out, is also exploring working with another engineering partner, specifically on the monitoring side. And so as we learn more about that from Windade, we'll make sure to communicate that to teams about if there's any change in scope or like things that we need to make sure we're collaborating with so that the system works as well from the components that are contributed from this other partner. All right, and that's all we've got. So I'll stop again for questions. Okay, well, it seems like there's no questions. If you guys think of any questions, I know it was kind of a lot of information to get at once. So as you read over the problem statement more, and access more of the technical resources, start figuring out what design decisions you might be considering, definitely just ask in the Slack. Anything if you want more research on a particular topic, want clarification on anything. We're here as like the technical organizers team to help you guys and answer any questions. Well, then I'll hope to see you guys again on Wednesday for the next one. The next one will be generator and overall like full system integration, including like thinking about scoring.
Thank you so much for today.
Yeah, happy to answer your guys' questions. Bye.
Bye.
Thanks for coming, guys. See you.